All right, let's get right into it. We all tend to think of empty space as, the simplest thing there is. It's just nothing. But what if I told you that this nothing might actually be the most complex, most fundamental thing in the entire universe?
Now that sounds like a question for a philosophy class, right? But it's actually one of the deepest and most challenging puzzles in all of modern physics. And believe me, the answer completely shatters our everyday intuition.
I mean, for pretty much all of human history, this was the obvious answer. A vacuum was just the total absence of stuff. A boring, passive, empty stage where all the real action of the universe takes place.
But then, quantum mechanics came along, and it paints a picture that is just radically different. It tells us that this so-called empty void is actually a seething, dynamic landscape, absolutely buzzing with potential and packed with hidden information.
So, what is empty space then? To really get our heads around this, we've got to compare the old, classical idea of a vacuum with this strange, wonderful, and frankly bizarre quantum reality. And the difference between these two views is, well, it's night and day. On one side, you have the classical void, a boring, static box. Nothing to see here. But on the other side, you have the quantum view. It sees the vacuum as a fundamental field, a roiling sea where these virtual particles literally pop into existence and then annihilate each other in the blink of an eye. It's not empty at all, it's alive.
Okay, so a thermometer for the vacuum. This all sounds great in theory, but it begs a pretty big question. If the vacuum is really buzzing with all this energy, how on earth could we ever measure it? How do you take the temperature of nothing?
Well, physicists have a brilliant little theoretical tool for just this problem. It's called an Unruh-DeWitt detector. The easiest way to think about it is as a tiny, perfect quantum thermometer. It's basically a simplified model of an atom that only has two energy levels, a low-energy ground state and a high-energy excited state. And its entire purpose is to interact with a quantum field and see if it can pick up any energy. So, here's how our little thermometer works. It starts out cold in its ground state. Then we just let it hang out and interact with the vacuum for a little bit. Now, if the detector manages to absorb a packet of energy, a quantum, from the field around it, it gets kicked up into that higher excited state. And that jump, that transition, that's what we would measure as a click. So a click is a huge deal. It means our thermometer found energy where we thought there was absolutely nothing. So let's put our quantum thermometer to the test. And I've got to tell you, this is where things get truly bizarre. We're about to see how something as simple as motion can literally change the fabric of reality and connect to things like heat, and even black holes. Okay, so first, let's imagine our observer, Alice. She takes her detector and just floats perfectly still out there in the middle of empty space. She's what we call an inertial observer. No forces acting on her, just coasting along. And the result? Exactly what you'd expect. Her detector is completely silent. Not a single click. From her point of view, the quantum vacuum is just cold, dark, and empty. But now, here comes Bob. He's in the exact same patch of space as Alice, but there's one critical difference. Bob hits the thrusters. He's accelerating. And all of a sudden, click, 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 Bob's detector just starts firing like crazy. For him, this supposedly empty void is not cold at all. It actually feels like a warm bath of particles. He is measuring real heat, where Alice measured absolute zero. This astonishing phenomenon is called the Unruh effect. It basically says that an accelerating observer will see the vacuum not as empty, but as a warm glow, a thermal bath, with a temperature that gets higher the faster they accelerate. Just let that sink in for a second. Your motion doesn't just change your location, it fundamentally alters the reality you experience. Now, here's where we make a huge connection. Thanks to Einstein's principle of equivalence, we know that the effects of gravity are indistinguishable from acceleration. So if accelerating through the vacuum generates heat, what do you think happens when you're sitting in the insane gravitational field near a black hole? Well, the logic leads us directly to a gravitational cousin of the Unruh effect, the famous Hawking effect. And the consequence here is just mind-blowing. It means that black holes cannot be completely black. The intense gravity at their edge has to cause the vacuum to glow, to radiate heat, and we call that Hawking radiation. This means that over immense, almost unimaginable timescales, black holes are actually slowly radiating away their energy and will eventually evaporate into nothing. Okay, so the vacuum has hidden energy that motion can reveal. But that is not all.
It turns out the void is also threaded through with a hidden web of quantum connections, which brings us to harvesting entanglement from nothing.
Let's set up one more quick thought experiment. We take two of our detectors and we place them really far apart. Then we switch them both on for such an incredibly brief moment that not even light, the fastest thing in the universe, has time to travel between them. In other words, they are totally causally disconnected.
Now, according to classical physics, there's absolutely no way they can influence each other. It should be impossible. But, and this is the key, they are both interacting with the same underlying thing, their own local patch of the quantum vacuum.
And here's the unbelievable part. When we check the detectors afterwards, we find that they've become quantumly entangled. Their fates are now mysteriously linked, even though they never ever send a signal to each other.
How is this even possible? Well, the detectors didn't create the entanglement. Instead, as the research puts it, they take advantage of pre-existing entanglement of the vacuum state. They are literally harvesting a quantum link that was already woven into the very fabric of empty space from the beginning.
So when you put all these pieces together, the hidden energy, the relativity of what's real, this pre-existing web of entanglement, our entire picture of nothing is just completely transformed.
So let's just recap the secrets of the void. We've learned the vacuum is not an empty box, it's a dynamic quantum field. We've seen that your motion determines whether that vacuum seems hot or cold. It's filled with a hidden web of quantum entanglement. And maybe the most profound idea of all, this quantum noise isn't just static. It actually encodes the geometry and the structure of space-time itself. Just think about that. It means, in principle, we could replace rulers and clocks with quantum probes that just read information directly from the vacuum.
So empty space isn't an absence, it's the fundamental canvas that reality is painted on. And that leaves us with one final, tantalizing question. If the vacuum holds the very blueprint of spacetime, what other incredible secrets is nothing still waiting to reveal to us?